Hello and good day everyone. I am Ken Ivan Bautista, and in this video I'm going to present to you my final project, my research study for the two subjects CSC113 Modeling and Simulation, and then the CSC175 Parallel and Distributed Computing, titled Testing Election Survey Simulating the 2022 Philippine Presidential Election via Monte Carlo and Parallel Computing. However, in this video, I'm be more focusing on the parallel and distributed computing side of my research. So, for introduction, we are living in a democratic country, and we know elections are one of the biggest events where regular citizens just like us have a say on who or how our country is going to be run by the government. So the reason as to why I've chosen the Philippine national and local elections of 2022 is that uh, that was my first presidential election, and the I feel I and there was the hype was there. The political engagement of regular citizen was an all-time high, and social media was exploding, and people don't really know who's going to win that election, presidential election, up until the results will come out. So you and I'll be more focusing on the surveys, the validity of the surveys, especially from the Pulse Asia and other organization, because before elections, the days leading to the elections, the surveys are the hot topic of the news, the social media, and even in the day-to-day regular conversation. uh, and they mostly used surveys based on age and socioeconomic status. So that's why these two demographic factors is I'm going to focus on in this simulation. So the main questions that I'll be asking in this research is: does parallel computing significantly improve the efficiency of the simulation? What are the limitations of the simulation when executed using parallel computing? And then, does Monte Carlo methods and parallel computing techniques can extract sufficient predictive power from these incredibly fundamental demographic factors? Review of related literature. So the first one is the I've mentioned in the uh, intro, the election and democracy in the Philippines. The influence and limitation of election polls just shows that sometimes, especially when predicting percentage based uh, surveys or events, uh, election polls and services have accuracy. Uh, so this is the reason why I have a hope for this simulation. And then the Monte Carlo methods in research election research. So since Monte Carlo is probabilistic in nature and voting is also probabilistic in nature, so the Monte Carlo simulation really fits this to be used in this simulation. And then enhancing efficiency through parallel computing. So since I'm going to be simulating hundreds of thousands of precincts and then millions of voters, so parallelization really is required, uh, like in the nature of the elections or the simulation itself. So the Amdahl's law, the theoretical speed up uh, of the simulation, and then since Monte Carlo simulation is highly parallelizable, so it is ideal to be paired with parallel computing. So theoretical background, I've mentioned the Monte Carlo simulation, and other researches such as by Tumibi and Olatukun used Monte Carlo simulation for random and uncertain behavior such as voting. And then the parallel computing simulation efficiency. So national elections, as I've already mentioned this earlier. to how the since the data sets or the required simulation is large, so parallelization uh, does play a crucial role in this simulation. So for the methodology, uh, parallel computation is also utilized. I've mentioned this earlier. At the same thousands of precincts and millions of voters at the same time. So since I'm going to be using processes here, since the simulation is CPU bound, it's computational heavy, a manager uh, will be set up to share memories for aggregating results and to be used for statistical analysis later. Uh, since they don't share memory by themselves and they need to have a uh, like centralized storage. So the steps are the creation of voters, which will be handled by Monte Carlo simulation, uh, assigning attributes for age and socioeconomic factors for each or socioeconomic status for each voter. Then the next is the assignment of probabilities, which is tackled in this modeling simulation part, but surveys have generates weight results or weights or probabilities into uh, how the chances of the voters choose specific candidate. So using those surveys based on age and socioeconomic uh, status, so they will be assigned probabilities. They will be assigned probabilities based on the voters' age and socioeconomic status, and then combine them to have a final probability or weights for selecting the specific candidates. Then the voting and simulation part, which will be also used by Monte Carlo, and this and the final is the tallying and analysis. So the first three steps will be utilizing parallelization, as these three steps are independent. Not independent, but they can each precincts are independent from each other. So these first three steps can be parallelized, and then the last step, which are the tallying and aggregating and statistical analysis of the results, cannot be parallelized. So this is the serialized part of the simulation. So the results and discussion. So I've executed the simulation twice. Once in for serial execution and then the parallelized execution. So I've uh, found that the serialized execution can run for 577.16 seconds, and then the parallel execution runtime is 177.87 seconds, which have a speed up time of 3.4 times. So using the Amdahl's law or the using the Amdahl's law, I've calculated the parallelized code and then serial code part, which is 73.79% and then 26.21%, which is related to these steps I've mentioned earlier. The 73% steps are can be parallelized, while the last one is serialized only. And calculating the limit of the sped up time, I've arrived at the maximum sped up of 3.82 times, which is the threshold or the maximum sped up regardless of how many processors you can add in the simulation. So accuracy comparison. So since parallelization is prone to deadlocks and race conditions, I I've validate the results by comparing the serial results, serialized execution results, and then the parallelized execution results, which you can see here in the graph are the same. I mean, not exactly, since uh, this is random. This simulation is random by nature, but they are relative with each other with minimal differences. The green one is the parallelized, and then the blue one is the serialized execution. Therefore, there was no race conditions or deadlocks that happened during the simulation, and therefore, the parallelized execution was the implementation of parallel execution is successful. Then, to further uh, provide evidence that the parallel implementation is successful, so I've run the uh, error metrics again, which I've used to verify the results of the simulation, that there are minimal differences uh, in comparing the serialized execution and parallelized execution. They have minimal differences in terms of the uh, error metrics that they have, that they error metrics of the results that they have produced. Therefore, further signifying that the execution of the execution of either serial and parallel uh, execution can have the same results, and the parallel execution uh, the parallel execution provided much better runtime and efficiency compared to the serialized execution. And the last one is the parallelization limits. So I've run two cases. The first one is the constant amount of processes, and then the last one is the variable amount of processes. So the first, I've run 10 trials here. The first one have 16 processes running at the same time, or at the same time, or 16 times 10 processes at the same time, so 160 processes running at the same time. So they have like similar run times for each simulation, while the case 2 have variable process from 17 to 116. So as you can see, the variable execution has a has an advantage for smaller processes, while the bigger the amount of processes it has, the bigger the runtime that it that it executes. Therefore, uh, the limitation of parallelization is that it doesn't matter how many processes you spawn. The limitation theoretically it can speed up more, but due to physical limitation of the machine, it will hit a threshold that it cannot provide more sped up, compared to when you have a constant amount of processes running at the same time. So in conclusion, on a technical level, multiprocessing worked incredibly well for handling massive electoral simulations. The experiment did show that the linear sped up is not always the result. Does not always result increasing in number of cores. Practical limitations are frequently missing from theoretical models, were introduced by elements like memory access bottlenecks and I/O constraints and interprocess communication. This results highlights how crucial it is to use parallelism carefully and optimally, which this study was able to accomplish. So that's it. That is all for my presentation, and Goodbye.